So we can summarize all of the phase changes that can happen on one graph. This is called a heating curve. In this case, we have ice, because this is for water, because from A to B is below 0 degrees. And so at atmospheric pressure and normal conditions, that means ice, solid water. Then it melts in the BC section. You'll notice the temperature stops changing. That's what I was talking about. Where we have plateaus, heat is still being added because our x-axis is still going up, but the temperature stops changing. And so this is where it's really, really important that you understand that heat and temperature are not the same thing. Heat is energy. Temperature is a measurement of average kinetic energy in the particles, right? So to go from a solid to a liquid, we have to break apart some of the IMF that are holding the solid together. That's where this heat is going. Until everything is melted, the temperature won't rise again. Once everything melts, then we start to get liquid water increasing temperature until we get to 100 degrees, which of course is the boiling point of water. Okay. We'll notice that the heat of vaporization is always much, much bigger than the heat of fusion. Okay, so this is the heat of fusion because it's going from the solid phase into the liquid phase. To go from liquid to gas is called heat of vaporization, and it's always going to be bigger because when you boil something, you have to separate every single IMF in that sample. Okay, that's going to take far more energy than separating just a few IMF to make the particles move around each other a little bit more, like they do when they're a liquid. Okay, so let's do this problem. When a question is asking for how much heat is required to transform ice to steam, we have multiple steps. This is a heat calculation, so remember that heat is Q, and it's typically measured in joules or kilojoules. And so we have to break apart every segment and do them separately. So you're going to have a Q of ice. You're going to have a Q of melting, which is also called fusion. You're going to have a Q of water. You're going to have a Q of vaporization. And you're going to have a Q for heating the steam. The ones that are increasing in temperature, we already know how to do. This is a review. Okay. The ones that are plateaus are just dimensional analysis, so nothing like shockingly new. I'm going to say when it's a plateau, which means flat. All right. And so these are the two strategies we're going to employ, and then when you're done, you just add everything up. I know that looks like a G. It's supposed to be a Q. I don't know why my tablet is doing that. It's a Q. All right, and so in order to do this, we're going to need to reference this data here. I want to point out something. Hold on, you can't see that. I want to point out something kind of important here. Our units don't match, so that's a hint. Okay, I'm going to open up a whiteboard so we have some space for this. Okay, so it doesn't really matter which order you do these things in, but I guess I'll just do the ice first. So I said anything where the temperature is changing is going to use Q equals mc delta T. So the first thing is we have to know the mass. This problem, poorly written, I wrote it, doesn't have a mass, so we're just going to make up one. I'm going to say it's 15 grams of water. Now, they might give you the amount of water or whatever substance in moles and then have you convert it, so that's a thing that happens. Remember that the symbol for mass is just M, moles is MOL. All right, so we need Q equals MC, and now, so this is the heat capacity of ice, not the heat capacity of water, right? So it's the same substance, but they have different abilities to absorb heat. We have only used 4.184 in our chapter 5 work, but it's important to understand that's because we were always working with water in the liquid form. Here, it's ice. So to decide what the delta T is going to be, we're going to have to think about that heating curve, right? So from A to B, B is at 0 degrees Celsius because that's the melting point. And our problem says we're starting at negative 10. So when you're figuring out the delta T, it's always the final minus the initial, right? And so here our final is 0 degrees Celsius. And we are subtracting our initial, which is negative 10. So our change in temperature is 10 degrees. We went up by 10 degrees. So that's what I'm going to put here. You'll note that I'm not using the 110 degrees because that wasn't ice, right? If you're at that high of a temperature, it's a vapor. So we have to think about this curve, the fact that we're going from negative 10 to 0 in this part of the equation. All right, and so then I think I will do the liquid water, which is going to be set up really similar, except my heat capacity will be different. My temperature is also going to be different, right? Because, so this will be the liquid in the purple. The liquid goes from 0 up to 100. So my delta T will be 100 degrees. Okay. Now for the gas, or the vapor if you like, our heat capacity is different again. It's just 2. Each phase has a different heat capacity for everything, not just water, for all substances. And so, so we have our boiling phase, and then our heating up the gas phase is going to go from 100 to our final temperature of 110. So that's a change of only 10 degrees. Okay. I'm not solving these because I think you guys can multiply, but this is how you set them up. Now, for the ones that are kind of new, we're going to go the heat of fusion and the heat of vaporization. And remember, sometimes we will also use enthalpy of vaporization because it means the same thing as heat of vaporization as long as pressure is the same. In this case, that value comes from your chart, right? So for vaporization, we're talking about boiling here. It's 40.68 kilojoules for every mole of substance. So all I need to know is moles, and then I can use dimensional analysis to figure out how much energy that will be. So to get that, we're going to have to go back to our mass of water and convert it. I hope by now you know how to show this using dimensional analysis. If you don't, the final will be treacherous. All right? Even if you get the right answer, by the way. So we have a total of 0.832 moles of water. So it's just dimensional analysis at this point. I know I'm going to have to add it to some units of joules, so I could either convert the kilojoules into joules, or I could take each of these and convert them. I make that judgment when I see what the answers are and whether they're very large in joules or whether they're small. If they're small, I'll keep it in joules. If they're large, I convert it to kilojoules. You could do that at any phase, though. You just need to do it before you add. So the fusion, so from solid to liquid, is going to be a different value. It's 6.02 kilojoules per mole. And we're going to multiply by the same amount. We're not changing the amount of water present. And however much that is will be the amount required to melt it, and we'll just add it to the rest of them as long as the units match. Okay. So that's how you're going to set up these problems. I'm not too concerned with the answers. It's a good idea for you to put them in and see if they make sense to you, but I'm not going to emphasize that here. You all need to be at a point now where you understand that the answer isn't the important part. The process is the important part. So when you get a question that seems simple like this, when you're talking about changing phases, you need to go, oh, wait, that's going to have multiple steps. They're not always going to give you the heat curve. So get in the habit of sketching one. They always have the same shape. And then it's handy once you've solved each step to write your variables in. And that way you know how much heat for each step there is, and you can add them together to get the total. So that's a heating curve problem.